The entire Cayley table for this dihedral group 3 sub 3 is on page 79. They call the capital RIs, they call them row I. And I in the example that I do with D4 later on, not now, I'm going to do it as soon, but in that example, I try to keep their language with using rows instead of R's and mu's instead of little r's that are traditionally used. So what is a Cayley table? Well, that's on page 43. And I'm going to show you by example what a Cayley table is. If I have just two elements, well, by properties of group, one of them has to be an E, an identity, because every group has to have an identity. So then I could start figuring out, just kind of like I had you playing with the equilateral triangle, I could figure out what goes in every one of these things. Well, identities leave things unchanged. So I know that E star A, for example, is A. I know E star E is E. I know A star E is A. I know, so I can figure everything out. The only thing that's kind of missing is A star A. What would that be equal to? Well, there's two possibilities, and we just shouted out both of them. So one could be E, and one could be A. That's the only two possibilities that are there. But if I get A star A is A, then A has to be E, because I'm about to prove to you that the identity is unique, right? There's only one identity, and I told you there's two things in the group, so it can't be the identity as well. So therefore, that only missing element must be A. E. Theorem 4.17 says E is unique. I'm going to prove that soon. But if I only have two elements, then I have this, and therefore I do know that that missing blank must be E. Well, then I can make a little table where I fill in all these things by whatever we do. We use our fingers to, nobody uses the phone book map anymore, right? But when I was young, we used phone book maps. Well, actually, my dad didn't use phone book maps, and he wouldn't ask for directions, and we were lost a lot. But there was a map in the phone book where you can actually go A, B, C, D, and 1, 2, 3, 4, and you can use your fingers and kind of, so that's all you're doing here. You're using your fingers, and E star E is this thing right here, E star A is this thing right here, A star E is this thing right here, and so forth. So you can actually see what the products are, and you could fill them all in. Now you can't do that with a blackboard, isn't that cool? So that's the only, and that was the only possible choice we could have had here, that E was there. We just figured that out. So that's called a Cayley table. And it turns out these Cayley tables are what we call Latin squares. And Fraley spends some time talking about Latin squares. Latin squares are so fun that you can get lost in just the Latin square part, and the rest of the class can go on without you. It's a lot of fun to start playing with the Latin squares and start looking at open problems on Latin squares. And I really caution you not to go online tonight and start looking at open problems on Latin squares, because I'm going to lose you for the rest of the semester. It's fun stuff. So I wanted to show you some other groups. The last time I taught graduate abstract algebra, I didn't have all the cool things like the braid groups. I only thought of that after we took the class, like, wow, I wish I had used more examples in class. But we did, our go-to example for weird example was the Klein 4 group. And so this is a group, this is the Cayley table for the group, and we're going to talk about that as time wears on. We're going to keep pulling this group back as a non-standard strange example. It's one of the examples that is not Z4. So Z4 is a group with 4 elements under addition. I'm going to hit that in a second. So you don't get Z4 because, well, it just turns out that it isn't Z4. But it's an interesting group. It's a finite group that's not cyclic. So that's what's really interesting. If you already had a decent abstract algebra class, and you remember they talk a lot about cyclic groups. It's not cyclic. It's a group of 4 elements, and it's not isomorphic to Z4. And this with the binary operation being plus. So let's look at number 5 on the in-class assignment. Actually, it's number 4. So inverse of A, B, and C, I'm going to bring that table back up. Just write the problem down, and I'll bring the table back up and just find the inverse by using the table.